So, yeah, I'll get started. So today, I'll be presenting my master's thesis work. The title of my work is Interfacing Circuits for Closed Loop in Plane Suspended Gate FET based accelerometer. So this is the overview of my today's presentation. I'll be introducing my work. Then I'll be discussing modeling of SG-FET device, design of all the different circuits involved in accelerometer system. I'll be discussing some of the design improvements that we have made. After that I'll be concluding my work, and in the end we have response to our reviewers' comment. So conventional capacitive accelerometers consist of proof mass which is free to move and a fixed electrode. The proof mass is anchored to the substrate and it is free to move. So when an external acceleration is applied, it will be applied on the proof mass. When it moves, the effective the distance between the electrodes will change, which will result in change in effective capacitance. So this can be used to measure the applied acceleration. So in this, the change, so to measure and detect the change in the physical quantity, which is capacitance, we have a capacitance to voltage converter and then an amplifier to amplify the electrical signal that we obtain. So this is the entire system of a passive capacitive accelerometer. So the limitations include, the limitations are as listed below. To obtain a better sensitivity, we need a larger sensor. So it consumes a lot of area, and also there is an extra C to V converter circuit. So due to these limitations, SG-FET based accelerometers have been explored as a better alternative. So in this, the transistor gate is movable and it is suspended. It is suspended and movable. So when acceleration is applied in this, in the example, in the block diagram, in the isometric view shown, the gate is free to move in plane, and when there is external acceleration applied, the gate will move, changing the effective width, which will result in change in total current flowing through the device, which can be used to measure the applied external acceleration. So here is the block diagram of the SG-FET based acceleration sensor. So this can be used. This will overcome the limitations of passive accelerometer. There is direct transduction. There is no need of C to V converter, and it has high sensitivity, and there is also inbuilt amplification. So now these transistors are modeled, and these will be used as sensors, and our system is designed. So first we will discuss modeling of these SG-FET based SG-FET based sensors, and then the design of circuits. The circuits are designed in cadence in UMC 180 nanometer technology. So we have used LUT based method to model the device. So first, MEMS plus. To simulate the MEMS structure, we have used MEMS plus. The simulation will give us all possible dimensions of transistor, all possible widths of the transistor for applied acceleration, and we have simulated this for a range of plus minus 5G. So using those transistor dimension values, mainly width values, we will do process and device simulation in TCAD for all possible transistor dimensions, and these will be extracted and modeled, and these values will be used in modeling the device. So we have written a Verilog A code which will read these lookup tables, and then all the values including the width are encoded as voltages. So the simulations which are needed to generate these lookup tables were done by Dr. Pramod from IIST under the guidance of Professor Sina, and we have used these values. So here is the lookup table model for SGFET. Acceleration input is given to MEMS LUT, which will give us the width of that transistor, and then that width is given as input to TK lookup table, which will give us the final current. So this is the open loop. This is the first stage of our system, which interfaces the suspended gate transistors, and here are the simulated results. So here we can see the drain voltage is saturating due to high gain, and the currents, the simulated results show input acceleration, effective gate width, drain current, and output voltage V1, V2 of this first stage. So now to obtain higher dynamic range, better sensitivity, we are operating in closed loop. So now we'll look at the block diagram of our closed loop accelerometer. The first stage is a differential amplifier which is interfacing IP FET, which we just discussed. Second stage is controller, and feedback path consists of charge pump which drives the actuator. So these are the schematic. This is the schematic of all the different blocks. The controller is a simple it is a GMC controller. The actuator is a differential cone drive actuator, which will be driven by differential high voltages VB plus minus V, and also actuator is modeled as lookup table, which was all the simulations were done in MEMS plus, and it is modeled using Verilog. And these two high voltages which are driving the actuator are generated by charge pump, which we will be discussing in detail in our further in our presentation. So now the cone drive, the actuator. Let's discuss the actuator briefly. So here, so when gate is displaced, the movement of gate is when it is in x direction. So when there is an acceleration applied and gate displaces, so to bring it back to zero position, the voltages VB plus or minus V is applied, which will generate the necessary force to bring the gate back to zero position. So those voltages, when this actuator was simulated in MEMS plus for an acceleration of plus or minus 5G, voltage up to 17 volts was required to balance the gate in mean position. So to generate those voltages on chip, we have used charge pump. So let's just discuss working of charge pump in brief. So the output of the controller is applied to the charge pump. The charge pump consists of transistors and capacitors, and it is driven by clock signal running at frequency of 50 megahertz. The clock is non-overlapping, and let's discuss both the phases of clock. When clock is low, then the NMOS transistor is on, which will connect input to the intermediate node. So the intermediate node charges up to voltage Vin, and when clock is applied in next phase, based on the parasitic capacitance at that node, it will charge up to a ratio of, it will charge based on the value of C0 and the parasitic capacitance, which we will be discussing further. So when after in the second phase, the intermediate node is connected to output. So the voltage, input voltage, and the input voltage is pumped by the voltage, by a value of VDD, and that is equal to our output. So one of the things that we have to note in this is the maximum voltage that can be generated by cascading multiple stages of CP1 is limited by junction breakdown voltage, junction J1. So here we have used triple well transistors. We can see cross section of CP1 in first figure. So the substrate and source are shorted to eliminate body effect. So the maximum voltage that can be generated by cascading multiple stages is limited by the breakdown voltage of junction J1. So to further extend the output, the range of output voltage that can be generated, we will be using charge pump type 2. Here we have used all transistors are NMOS transistors, and the substrate is connected to a higher potential. So now we can extend the output voltage that can be generated by a value which is equal to the junction breakdown voltage of junction J2. So next thing, so now we will be cascading multiple stages of CP1 and CP2, and we will be generating high voltage which will drive the actuator. But we should also note that there is a need to control the output voltage that is generated, because it should be proportional to the input acceleration, and also there is no path for discharge when input reduces. So these are the things that we should note while we are designing. So the output voltage is given by Vin, governed by that equation Vout. Vin is the input voltage, N is the number of stages that we cascade, C0 is the capacitor that is coupled with clock, and Cp is the parasitic capacitance at the intermediate node, and V5 is the voltage of clock signal. So now to control the output voltage generated, we can either vary the number of active stages, or we can vary the ratio C0 by C0 plus Cp. So now to generate one thing, when clock is not applied, Vout will charge up to Vin through leakage current. So let's say we have cascaded the required number of stages and we need the minimum voltage. Then it will be one of the charge stages is active and the others are all inactive. Then the output node has to charge to the value of input only through leakage current. It has high latency, which is not suitable for our operation. That is why we will be varying the ratio C0 by C0 plus Cp to control the output voltage generated. So that is done by connecting or disconnecting capacitors to clock signal. So when we need the highest efficiency, we will be connecting all the capacitors to clock, which is done by varying the digital word Q. So we have a separate digital block which will be generating the digital word Q, which we will discuss later. So these are the simulated results. The minimum voltage generated is around 4.7, and the highest voltage we need is 15.62. We have cascaded 4 stages of CP1 and 2 stages of CP2 to generate these voltages. And now next thing is there is no charge pumps don't allow the reverse current flow. So we have a discharge stage that will facilitate the discharge of output node when input reduces. So that we have designed using for that we have stacked transistors which will be driven by the intermediate voltages of multiple stages of charge pump. So we have chosen voltages such that none of the transistor junction break down. So the current through the discharge stage is always on, and the current flowing through the discharge stage is half of the forward current. So when the input is reducing, there is 2 times the discharge current flowing through the forward path from input to output, so which will charge the output node, and when the input reduces, the output node will discharge with current I through the discharge path. So now there is a need to monitor the common mode voltage of these high voltage charge pump. So to achieve that, we have designed a common mode feedback loop for charge pump. Here we'll be monitoring, we'll be looking at the drain voltages of last transistor in the transistor stack, and we'll be comparing that with the reference, and we'll set the gate voltage of the last transistor. So this is the complete schematic of charge pump with the digital loop, which will be generating the digital word Q, which controls the voltage generated by charge pump. So the digital logic will look, the digital logic takes reference, the digital logic takes input from the integrator, which will be compared with reference. So based on that, the digital word will be incremented or decremented to change the output voltage. So this is the complete schematic of our closed loop. We have first stage interfacing lookup tables, controller whose output is given as input to charge pump, and digital logic. And the final lookup table in our closed loop system consists of MEMS lookup table of both transistor and actuator. So this lookup table will take input acceleration and the output voltage of charge pump, and it will give effective width as input to TCAD lookup table of SG5. So this is the entire system. So these are the simulated results. First one is a sine input of range plus minus 4G at frequency of 100 Hz. We can see that width is at constant 10 micrometer, and also the output voltage of both the charge pumps are also shown. And now that we as we just discussed, we saw that there are lookup tables, switching circuits, analog circuits, and it covers all the different multiple domains are covered. So to analyze the stability of this closed loop in a conventional way is so to analyze the stability, we have not followed the conventional way. Here we have given a step input, and we make sure that when we make sure that the output does not have any ringing to ensure the stability of closed loop. So there were some we have also presented some design improvements in our closed loop. So let's first discuss some of the limitations that are present in the design that we just discussed. So we saw that the output voltage of charge pump simulated results of the output voltage of charge pump. We can see that latency varies over a wide range. So simulated results were at least efficiency, the latency was around 430 nanoseconds, and at highest it was 70 microseconds. So it is necessary to improve reduce this variation because this will lead to inaccurate common mode voltage measurement. So the highest voltage will settle faster than the output voltage of the charge pump, which is at lower efficiency, which will lead to inaccurate common mode measurement. And also the discharge state, which is just a stack of transistors, it's driven by the voltages from the intermediate stages of charge pump. What happens? These voltages are not same for both the charge pumps which are generating the differential signals. So what happens? The effective resistance of the discharge path is not same for both the charge pumps. This will also lead to inaccurate common mode measurement. And also the lookup table that we have used, the lookup table, the model for actuator is not capturing frequency dependent behavior. So let's discuss these one by one. Why why the results are the way. We'll discuss why it is the way. We'll discuss why it happens, and then also how we have modified our design to improve. So first one is latent variation. First one is latent variations in the latency of charge pump. So this occurs because we saw that we'll be adding multiple capacitors in parallel when we need when we have to increase the output voltage generated, and we'll be disconnecting them from clock when we need lower voltage. So that means the voltage V1 that the intermediate node sees, V1, let's say V1 is the voltage the intermediate node sees at least efficiency. So the dot voltage from our simulations is equal to 0.5 volts. So that is the VGS for those transistors, and at highest efficiency that voltage is higher. So from the equation which is given below, the RDS is not constant. So now this will change the time constant of charge pump, due to which these variations occur. So now to avoid this, here in the simulated results we can see that the charge pump varies, and then it is back to the right value, and that is because it settles later and we have common mode feedback. So now to avoid this, we have used bootstrap switches which will maintain gate to source voltage constant. These are the schematic of CP1 and CP2 with bootstrap switches, and here we have the simulated results also. We can see that latency variations are very less, and those slight variations are due to M3 and M4 diode connected transistors in CP2. And second was the effective resistance of discharge path, which is not same for both the charge paths which are generating differential voltage. So to avoid this, we have used multi-level converters, and I would like to thank Professor Abhijit for all his inputs related to multi-level converters. So multi-level converters are DC-DC converter circuits. So by properly with appropriate switching sequence, we can set the output voltage to required voltage level. So let's discuss briefly about that. So let's say both switches S1 and S2 are on, then Vin is equal to Vout, and if both are off, then the switches which are given by signals S1 bar and S2 bar will be on, and there is a discharge path for output, and output is equal to 0. So if we set proper switching sequence, here we have shown the other. If we choose a switching sequence where S1 is on 50% of the time, then the green path shown is the path from input to output, and Vout is equal to Vin minus charge of the capacitor. And when the switches are driven by the complementary signal, Vout is equal to charge on the capacitor. So if we switch constantly between these two states, then we can have a output voltage of Vout output voltage which is equal to half of Vn. So now if we use this to step down the output voltage of charge pump, the maximum voltage goes up to 70 volts in our design, and the output voltage that we obtain is equal to 8.5 volts, which is greater than VDD, and it can't be used to measure and set the common mode voltage, and also it will lead to breakdown of transistors, breakdown of junctions of switches S1 and all the 4 switches. So we will be using a 7-level converter as discharge stage. So these are here we have the gate signals that are driving the transistors which are switches, And also we have made sure none of the transistor junction breakdown, and also output is less than VDD. So we will be using this output voltage to set the common mode. We will look at the output voltage, and we will drive the gate of the gate signal V discharge to set the common mode output. So these are the simulated results with multi-level converters have discharge stage. First one is at common mode setting, and second is at a differential efficiency setting. And third one was the actuator lookup table, which the current, the one we discussed previously, does not capture the frequency response. So instead we have designed circuit using passive components, which will have the same transfer function as the actuator. So here we match the AC response of actuator and we design a circuit. So here we have shown the block diagram of the circuit which is designed using passive component. So we have LC tank in parallel with low pass, which will have the similar response, AC response as the actuator, and also I've shown the simulated results in cadence. So this design was submitted to Unicas 2023. And the proposal was selected. So we have we plan to fabricate the ASIC, which is marked below. So the IP FET sensor and the actuator will be external to the chip. The differential amplifier interfacing the SGFET integral controller at charge pump along with its digital logic was to be fabricated and tested. So we have used all the open source tools in designing, and sincere thanks to Pranav for his involvement and contribution in completing the layout of our design. So this is the complete layout, and layout dimensions are given above. The design was done and it was simulated in Skywater 180 nanometer at a supply voltage of 1.8 volt. And in this section, I'll be presenting post-layout simulation results of different blocks. This is the post-layout simulation. These are the post-layout simulation results of integral controller, and these are the schematic and post-layout simulation of charge pump at CP1 at 3 different efficiency settings. For an input voltage of 0.9 volts. The 3 different settings are highest, lowest, and common mode efficiency setting. And these are the post-layout simulation results of CP2 at 3 different efficiency settings for an input of 9 volts. So these are the conclusions from my work. So here we discussed that SGFETs are better alternative to passive capacitive accelerometers, and we also discussed and presented the simulated results of interfacing circuits and closed-loop accelerometer. The closed-loop accelerator simulated results for 2 different inputs were also presented, and also post-layout simulation results for our design in Skywater 130 nanometer were presented. Future work, the SGFET models which we have used, the lookup tables, they don't include parasitics and noise performance of SGFET. So better models which consider these should be used in simulation. And also the quantitative analysis of temperature dependence of charge pump should be done. And also all the designs, all the results presented were circuit simulations in cadence. So we have submitted our design again in this year's, we have submitted a proposal again So we plan to fabricate and measure the results, and also to further extend the output voltage generated by charge count, we can use pin diode based charge count, and also those should be designed to optimize the latency. I would like to thank all the audience.